All right, we're back. So video number 6 now. We're going to continue talking about concave mirrors. So this is the second example. And the way that this example is going to be different is we're still going to have a concave mirror. So the surface of the mirror is still going to be reflective, except now we're going to take the object and we're going to put it in front of the focal. Last time it was over here behind the focal, and we'll see how things change. I'm going to use similar numbers and similar formulas to what we did last time. All right, so to review, in the first video on light and mirrors, we talked about how r, the radius of the curvature of the mirror, is equal to 2 times the focal length. We also talked about the 3 ray rules for all things, lens, mirrors, whatever. We come in parallel, we leave based on the focal. Then we come in for our ray based on the focal and we leave parallel. And then finally, we come in from the top of the object to the origin and we must leave at an equal angle. The reason this one works is it's the only flat part of the curved mirror. Last time we also talked about the lens maker's equation. Lens maker's equation says 1 over the focal length equals 1 over the distance to the image plus 1 over the distance to the object. Then we also had the magnification equation. Magnification is equal to the height of the image over the height of the object, which is equal to the negative distance to the image over the distance of the object. So that's a little bit of a review of the formulas that we've been working with. So last time we kind of had a situation where we had an object, and the object was located behind the focal. So the focal was 5 and the object was 8. And now we're going to put it here at 3. And we're going to see what happens, how it's going to be different, okay? So let's put in the x-axis. Here it comes. Let's put in the y-axis. Okay. I'm going to show that this is concave by curving the ends. And then I'm going to go through and put in some reflection so we can see which side is reflective. I told you last time that the focal length was 5. The focal length is still going to be 5. So I'm going to write that up here. So I'm going to say focal equals 5. And then we're going to go ahead and put in the object distance, but this time the object isn't going to be 8, it'll be 3. Let's keep the height of the object the same. We're essentially moving it just in front of the focal. So I come over 1, 2, 3, 4, 5 focal length, and I come over 1, 2, 3 object. The object's height is 3. So when the rays leave the object, remember they're going in every direction, and we're only going to concern ourselves with 3 of these rays. And these 3 rays that we're going to concern ourselves with do these 3 rules. And so the first one comes in parallel. So we come in parallel, just like we did last time. You come in parallel. Now, because of the curvature of the mirror, we're going to be bent down right through the focal. And you'll see this looks very similar to the last time that we did it. For our next ray rule, we have to come in based on the focal and leave parallel. Now the application of this rule is very different than the first application. I must line my ruler up with the top of the arrow and the focal length. I don't actually go through the focal. It's based on the focal. So I'm going to come in like this, and then I'm going to leave parallel. Watch how I'm turning my ruler. I'm turning it horizontally so that I can leave. And that's exactly what I'm going to do. And I'm going to just come on back. And you might be thinking, hey, those are never going to intersect. And you are 100% right. They are not going to intersect. And so that means that this is going to be virtual. This is going to be a virtual image that we're going to form. It's only going to appear in the mirror. It won't be able to be projected. It's virtual. Our last Ray rule says go in through the origin and leave at an equal angle. This one works because this is the only flat part of the mirror. So we come down through the origin. This is where I messed up last time. Count down 1, 2, 3. Let's see if I got it right this time. And then we're going to come back exactly like this. Put some arrowheads on. Once again, it confirms the fact that it's virtual because they're never going to meet. So what do you do? What do you do when it's virtual? We have to see where they would meet. So we're going to trace the reflected rays back. And that is what I'm doing right now, is I'm just tracing that reflected ray back. There's my first ray trace back for reflected rays. Now check this one out. The purple one, the one up here on top. We're going to bring him back. Just like this. Okay, last but not least, we're also going to do it for the original ray. Take the reflected ray. Oh, that's nice. And trace it back. That intersection is where we believe the image will be forming. So I'm going to take my ruler and just draw and label I for image. So when we look into the mirror, it's going to magnify it, kind of like a shaving mirror would, or a compact mirror. It gives you a close-up look of what you're looking at, but you can't project it. So it couldn't be used as a projector or something like that. It can only be seen virtually. Okay, so time to count some stuff, right? We've got the givens, that's this, and then we got to solve, we got to measure some things. That's the graph. All right, here we go, graph. And so what are we're gonna measure? We're gonna measure the distance to the image, some number of centimeters. We're gonna get the height of the image, and we're gonna get the magnification. Remember, times is always how we express. Let me move this down just a little bit. There we go. All right, so let's count over 1, 2, 3, 4, 5, 6. So this is on the negative side of the mirror, so we must label it -6. Yeah, virtual. Height of the image, 1, 2, 3, 4, 5, 6, 7. Height is 7. Magnification, well, it's going to be greater than 1. We got kind of like 7/3 going. Take that down to decimal form, 2 1/3, 2.33. I'll just write it like that. And that would be the magnification, 2.33. Great. So now we have our graph answers. Let me label it graph for all to see. Graph. Now we got to go through and solve them again, but we got to do it with math. Oh yeah, math. I said it. We're going to do it. So now we got to do formulas. Yes. Of course, physics, formulas, they go together. So what formulas do we want to use to do this? Well, the first formula we're going to use, we'll just find the radius of the curvature of the mirror. So just like it was yesterday, r equals 2f. Now this time it's negative, so we'd say 2 times -5. The radius of the curvature of this mirror would be -10. No, I said that wrong. +10. It's got the same answers as before. I don't even think I put this as a choice on the problem set for that reason. All right, so we have positive focal, +10 for the radius of the curvature of the mirror. Another thing we talked about is the Lensmaker's equation, 1/f equals 1/di plus 1/do. So we can take things from the yellow post-it note up here, the givens, and we can plug them in for what we can here. So we're going to put in -1/5, solving for di, plus 1/do, where do is 3. Find a common denominator between 3 and 5, that's 15, so we get 3/15 here, equals 1/di plus 5/15 over here. So what do? We try to get 1/di by itself, so we subtract by 5/15 on both sides, giving us -2/15 over here. And then what we want to do is we want to flip the whole action here. So we flip it on its end and get di on top. So we get -15/2, which is -7.5. Let's take a quick comparison to our graph answers. Once again, I'm not doing so hot on my graphing. I was off by 1.5 centimeter. This is the right answer. How do I know? It's math. It's exact. That means I had errors in my graphing. Sad day. Okay, so that's the first thing. Let's kind of make a little post-it note for our math answers as well, I guess. So we had graph answers, and now we're going to have math answers. Math. Okay, and the first thing we got from math was negative 7.5. We had negative 6. This is negative 7.5. Now we got to find some other things like the height of the image and then the magnification. Alrighty. So my magnification equation, you might remember from last time, looks like this. It's an equals business. So we have HI over HO, and we have negative DI over DO. What I'm going to do is I'm going to put in 7.5, negative 7.5 on top, DI. DO was given to us. DO was given to us, and it was the distance away right here, and it was only 3. So, basically what we do now is we just kind of simplify. So we'll just use our calculator to help us with this. So we're going to take negative of a negative, which is positive, 7.5 divided by 3 is 2.5. So the magnification we get is times 2.5. Notice that it's greater than 1. That's important. That explains why our arrow is bigger than the original arrow. The arrow of the image is bigger because magnification is that high. So I'm going to put that in right here, 2.5 for m, and then we're ready to solve for hi. So using this number 2.5, it also equals hi over ho. Now remember, ho was given at the beginning. Let's take a look. Ho is 3. So if we make this 3 and we multiply it by 2.5, we get 7.5 for the height of the image. Which is weird because that's what di was, but that just worked out that way this time. Probably because it was 3 and 3, and that's why we get 7.5 and 7.5. So the height of the image being 7.5, put that in here. Let's see how we did. Let's look at our graph answer. Oh, a little bit better, 7, pretty close. Now, which ones do we use when we're going through and taking the quiz? Do I use the graph? Do I use math? Like which? These are better, okay? As long as you don't make any math errors, these are going to be better for you. They're exact. You won't have anything off. Although I do accept acceptability ranges, so it's possible you could graph it and get the right answers on the quiz and not do the math at all. Or, likewise, it's possible on the quiz you could do all the math answers and not do any of the graph, and I'd never know. Except you have to, on the problem sets, attach pictures of what you did. On the quiz, I'm just like, pick which way works best for you. So that's how we approach this problem. Now we have to describe it. Okay, so we've gone through and we've got our math answers and we got our graph answers, and now we're ready to kind of describe things. Let me put my givens in here too. This will be a party, a post-it note party here. So how would we describe this? Well, let's think. Is it real or virtual? This is virtual because the image is forming on the negative side. If we're using just math answers, see the negative sign in front of di? Therefore, it's virtual. So this image is virtual. It's not real. Secondly, I have to just say if it's erect or inverted. Okay, this is erect. Look at the direction of the arrowhead. It's pointing up. That is erect. Okay, how else do I know? Look at the sign of HI. It's positive. That's how you can tell as well. So it's going to be erect. Finally, enlarged or reduced. Enlarged or reduced. Look here. See how it's bigger? Okay, it's enlarged. Secondly, if we look at the math, see the magnification? It has a magnitude greater than 1. That means enlarged. You can also just compare the heights. See the height? It was 3. Now it's 7.5. Enlarged. So when we describe this image, we'd say virtual, erect, enlarged. And that's how we would describe it. Now, let me see if I can find what we did last time. And let's make a comparison here. So this was when the object was behind the focal. See the image here? It is real. It was enlarged and it was inverted. And then when we move the object in front of the focal, notice the change. Now it becomes virtual, it becomes erect, and it becomes enlarged. So, just something to notice. Every time is a little bit different. The one thing that stays the same, however, are array rules. So, just realize these will work all the time. It's just going to be applied a little bit differently. All right, so a good thing to do would maybe be to do the front half of the problem set at this point. That's kind of where you want to be, is completely done with the front half of the problem set. Then I'm going to wait till tomorrow to make some more videos here for convex, which means we take the curvature and we point it the other direction. All right, thanks for tuning in. We'll check in with you with the next video.